So this is just a reminder of how to do, or what is a basic integral, how to do basic integrals. So let's say that we have a graph and we're graphing force versus displacement, and the force increases like in a spring. It increases with displacement from equilibrium. And we want to know the work done. The work done for a constant force is F dot dx. Whoops. F dot x. But for a non-constant force, right, the question I always like, do you use this force, do you use this force, do you use the average of the force? And the answer is none of the above. What you need to do is think about it this way. So the work in general for a constant force, well, we've seen that the work is the area under the force displacement graph. How do you get the area under? Well, this one's easy because it's just a triangle, and so we could say that the work here would be, just jumping ahead, if this was F final, F initial is 0, the work done in this case is not, right, it's not FFX, nope, it's the area under the triangle, which is 1/2, oh, I guess I didn't say this either, X final, 1/2 F final, X final is the area of that triangle. Anyway, so let's see how that works out, how we can actually work that out without actually drawing a graph and taking an area of a triangle. So the concept is to say, oh, okay, so the force is not constant. So let's just take a small piece of this triangle. Let's go ahead and just look at a small piece of this triangle. And so since it's a small piece, instead of it being a width, delta x, we're going to say it's a width, dx, because remember the difference between delta and d. Delta means change in, and d means small change in. That's a mathematical thing. Okay, so that's just a little dx. And let's take the area of that sliver. The area of that sliver, let's color it in red, is that right there. And say, okay, well, there's still a little bit of a curve at the top, so it's not exactly a rectangle. Oh, and let's say the F at that point. That's just some intermediate F. We'll just call it F. But if we take a small enough sliver, as long as it's small enough, doesn't matter what shape this curve is, right? And I just chose a flat line, but this could be some curvy, crazy line. If we take a small, right, I mean, it could be a curvy, crazy line. Let's draw a curvy, crazy line. Curvy, crazy line. Whoops, that was red. Curvy, crazy line. That could be my force versus x. And we're still trying to find the area under it. But if we take a small enough sliver, we can approximate this. Okay. Since I made a mess of my graph, I just took the sliver out, right? So this is my sliver. We can approximate that top bit as being flat. See, but how can we do that? Well, as long as the sliver is small enough, dx, it's a small change in, we can approximate that top bit as being flat. And really what we want to do is we want to just do the operation that we're about to do to the limit where dx is infinitesimally small. And if dx is infinitesimally small, then it's perfectly good approximation to approximate that top bit as being flat. So therefore, the area of this little slab, which is just a little bit of the work, so we'll call it d work, the area, which is going to be the area of this little slab, is going to be F times dx. That's the little piece of work there. What we're going to do is, what you might guess we're going to do, is we're going to go ahead and just take a whole bunch of little slabs, and we'll do this one. Say there's d work there. It's a different amount of work. This one, d work there. It's a different amount of work. This one, d work there. It's a different amount of work. And so we'll calculate, so there's going to be all these different f's, and I guess I'll call them f sub i's, not as an initial, but that there's f1, f2, f3, f4, f5, etc. And in the end, we're going to say d work let me just do that differently. We can just break it. We can say, well, there's one slab, d work 1 is equals F1 d1. So we can call this F1, and this F2, and this F3, etc. And so d work 2 equals F2 dx. We're just always taking little dx's, the same length each time. So that therefore the total work done is d, once we break it up all the way down and all the way up, is dw1 plus dw2 plus dw3 plus add them all up. So we can write that with a sum sign. That's sum sign. So we're summing over I of dwi. Okay, so I is just an integer. And that is the sum over I of fi dx. So now summing it up or making a neater picture, so this is where we are. We've got the work under the curve, which is the whole green area, is equal to the work under that little red area, added up when we make a whole bunch of, we add up, we just move that little slab over, keep moving it over from x equals 0 to x equals x. Okay, and then we say, okay, this is going to be approximate. This is approximately the work because we are approximating that, that the force is constant for this little slab. But as long as we make dx small enough, and small enough is infinitesimally small, then it's going to be exact. So I guess we sort of write that work is, that the work is approximately that, and if dx goes to 0, right, infinitesimally small, therefore the work is exactly that. But when dx goes to 0, then it's an infinite sum, right? Where it's if dx goes to 0, we're going to have an infinite number of these little red slabs. And so that is when we change the sum symbol. This is an infinite sum over infinitesimally small. An infinite sum over infinitesimally small dx's. And the sum symbol turns into an integral symbol. The integral symbol, that sort of stretched out SE thing. And so, and we also, just for notation wise, we integrate from our initial x, in this case we started from 0, to our final x, in this case we said we were just going up to some x final, and we just put those limits on the integral just to make sure we understand that we're integrating over the x variable. That's the one that we're adding up. We're adding up, we're adding up as x gets bigger. So that's our integral variable. Now, f sub I, now because this is infinitesimally small and now we're just tracing, we're saying, okay, really what we're doing is we're adding up the area of this plus the area of this. So it's really a single line, and we've got an infinite number of lines. F is just the function itself, f of x, right? So this f sub I actually turns into, so this wasn't actually quite correct, f sub I actually just turns into f of x dx. So f is a function of x. And so that is the work done under a curve, under a force displacement curve that is not constant. So again, so far all I've done is defined the concept of an integral. That the work done by a variable force, a force that varies with x, is equal to what's called the integral of f of x dx. Of the f as a function of x dx. So we're integrating over x. So one important thing with all integrals that you got to always pay attention to is that since we're integrating over x, everything else has to be written. Everything in the integral has to be written in terms of x. If there's a constant, it doesn't matter because the constant can just be, we don't have to worry about that. Constants just come out of the integral, just like they would out of the sum. But the functions have to be written in terms of the variable of integration, in terms of x. So this is why work is the correct definition of work. And I just did this in one dimension. So we can just go ahead and say, therefore, in any number of dimensions, the correct definition of work for any force, variable or constant, is the integral of f dot, you can call it dx, but if we're allowing for 3 dimensions, I would just call it some other variable where ds, right? ds could be dx, or it could be, right, dx, which is in the I direction, or it could be dy, which is in the j direction, or it could be dz, which is in the k direction. That's why we just use ds, because it allows for 3-dimensional, us to do in 3 dimensions, right? So ds is just a position, it's a displacement vector. It's a displacement vector, right? It's like saying s, the displacement vector, has a component in the x direction, a component in the y direction, and a component in the z direction. But we're just taking the infinitesimally small displacement vector. Okay. So let me just make sure you realize that if f is a constant and if the angle is a constant, in other words, if this is our typical kind of problem where we're dragging a box and theta doesn't change and f doesn't change, then this basically looks like we can pull the f and the dot product, right? Because the dot product is just cosine theta. Ooh. Let me rewrite this. Dot product just gives us that. There's nothing new here. That's the dot product. If f and theta are constants, then we can pull them out of the integral. If they do not vary with s, if they do not vary with our position variable, we can pull them out of the integral. S is still our integration variable because it's still a ds, but the integral of ds by itself is just s, f cosine theta, and that's the answer to the integral. And so therefore, if you don't actually have to integrate over a function, the integral of ds it's actually delta s, right? It's s final minus s initial. But we write that as s because we usually think s initial is 0. And so it's just fs cosine theta, or it can be written as f dot s. Okay, so that's for a constant force, right? For a constant force in a constant direction, or just for a constant force. There you go. And so we get back, so the integral is the most general definition, because if it's constant, we get back just f dot s. Okay, so how do we do integrals? So now we know how to set it up, but then you say, okay, so I said I'm given an arbitrary function, right? Let's say somebody tells me the force is 3x squared plus 2x plus 1, and the displacement variable is x, and the angle between them is 0, so we don't worry about the dot product. So let's just say we're doing this example from x initial to x final. How do we do that integral? So now this is the math part. I guess in a sense this was sort of a physics part, but it was more really just an example showing the math of what an integral is. How do we do the math part here? So an integral, so this is the math part. I'm going to skip the theory and just give you the tools. An integral is an antiderivative. That's what you got to remember, is that if you know how to take a derivative, you know how to do an integral, because it's just the opposite. We're just doing the derivative backwards. And so remember, if the derivative of 3x squared is equal to, right, we pull the 2 down, 2 times 3 times x to the 2 minus 1, so that's 6x, then the integral of 6x is equal to 3x squared. Now we still have to evaluate it from x0 to xf, x0 to xf, so first of all, the integral is the antiderivative. It's the opposite. It's going backwards. But then we have to evaluate it from our limits. And what that means is we evaluate, if we're going from x initial to x final, what that means is that you evaluate it at the top limit, 3, you just plug in x final squared, and you subtract from it evaluated at the bottom limit, x0 squared. And this line that I drew here, I didn't explain that. Again, this line, this is just common mathematical notation. It says I've done the integral, but I haven't evaluated it yet, and we still have to evaluate it from xf to x0. So this is the integral of 6x. So it's 3x squared, but evaluated at our limits. Okay, so let's say in general, so therefore, in general, since the derivative is in general, let me change my color, A general derivative is if you have, I don't know, if you have ax to the n, therefore d dx, if we have a function f of x equals ax to the n, then d dx of f of x is equal to n a x to the n minus 1, right? We pull down the exponent and we subtract 1 from it. Then therefore, the integral of f of x dx is equal to the opposite, right? If a, again, if a x to the n, so I'm not taking the integral of this, but I'm taking the integral of this. If f of x is a x to the n, integral is the function, we have to add 1 to the function, to the exponent, and we divide by that number, right? That's the antiderivative. So the integral of ax to the n is ax to the n plus 1 divided by n plus 1. That's it. That's it. You really need to know to do integrals. Now it's true that we've got, that's for a standard function, a polynomial function. That's for a polynomial function, as opposed to, right, we can talk about the integral of sine theta, cosine theta, etc. Well, if you know how to take the derivative, you know how to take the integral, because if the derivative of a sine is a cosine, then the integral of a cosine is a sine. But all we care about for now in this class is the standard polynomial functions. So let's just go ahead and, as a last thing, let's just take this this example and go ahead and do the integral. So the integral of this is, we take this polynomial function 3x squared and we raise it to 1 more power, so it's 3x cubed, and we divide by the power 3. Then let's integrate the second function. 2x, we raise it to 1 more power, 2x squared, and we divide by the power 2. And then we take this third function. That's 1. Now remember, that's x to the 0, right? The x to the 0 is 1. So it's 1x to the 0, so now we're adding 1 to the power, so 1x to the first divided by the power. That's our integral, but we still have to evaluate it from x0 to xf. And so we end up getting, oh look, I didn't mean to make it 3, 2, 1. That was stupid. Sorry. These remember, these exponents out front are completely arbitrary. But I didn't make them really arbitrary. I made them 3, 2, 1, which was stupid because it just, there's nothing special about them. And so the answer here is 3x is x cubed plus x squared plus x. Yes, x squared plus x cubed plus x, and then we evaluate it from x final to x initial, from x initial to x final, which means therefore the work is equal to x final cubed plus x final squared, squared, x final squared plus x final minus, it evaluated x initial cubed plus x initial squared plus x initial. Okay. But after all that, I was just showing what integrals were. This is what you need to know how to do. Bye.